Hello and welcome to this tech talk for controls for managing events in serverless applications. My name is Ben Smith and I'm a senior developer advocate for AWS Serverless. You can follow me on Twitter at Benjamin_L_S if you so choose. So let's jump straight into it. We're going to be covering three key topics today. Primarily, I'm going to talk about the basics of event-driven architectures and some best practices for adopting this paradigm yourself. I'm going to provide an introduction to Amazon EventBridge, which is a new serverless event bus. And we'll look at how that service works and how it fits into some of the concepts I cover in the first section. Then we'll talk about asynchronous event invocations with AWS Lambda and some of the new controls that have been put in place to help you manage them. Finally, we'll take a look at stream processing Lambda invocations and see how you can take advantage of some of the new controls to best manage failures and retries. So let's get started. If you've been to an AWS conference before, you've probably seen a slide that looks a bit like this. But I'm here to tell you that monoliths get a bad rap. Monoliths are easy to build and reason about. It can be simpler to understand how the system is going to work when all your data is in one database and the calls you're making are operating against the same memory space. Distributed systems of microservices can be more complex, but the problem is monoliths don't scale so well, both in terms of throughput as well as the teams that support them. If you have big, complex systems and you want to be able to effectively leverage dozens or hundreds of engineers to build features in parallel, you have to move to the microservices model. Now, this isn't a tech talk on breaking monoliths, so I don't want to spend too much time here, but I think it's really important to recognize that all these cool new architectural paradigms, including event-driven architectures, are really in service to these fundamental goals. We want to enable teams within larger organizations to be able to build valuable features for their customers and to do it in a way that's reliable and resilient and scalable. And we want them to be able to deliver all of these things quickly. So really, the goal of this tech talk is to show you how you can make use of event-driven architectures and some new Lambda controls to help achieve those goals. Here, we have a representation of a simple architecture that serves orders and invoices. When your architecture looks like this, a command-orientated design with synchronous API is fine. But what happens when you start adding more services in to integrate with the first order service? What's problematic with this API-orientated design is that the order service needs to know about all these other boxes. We'll talk a lot about how great microservices are because they are decoupled, but the order service needs to know how to locate these other endpoints. It needs to understand how to make the appropriate API calls, what to do if one of those calls fails, and it needs to have the appropriate retry logic and error handling and all that other stuff baked in for each of the services it talks to. And long term, there are going to be more systems out there that need data about what's happening with customer orders. But with this model, those teams are beholden to the order service team to implement that for them. And remember, our ultimate goal here is to help enable our teams move fast. But now there's an unnecessary friction in the process due to the integration cost of hooking these services together. So let's take a look at how this system might differ if we use an event-driven design. First, I should probably define a bit more about what I mean by an event. In the simplest of terms, an event is a signal that a system's state has changed. In most modern systems, these are represented as a JSON message that provides some set of facts about what changed and potentially what the current state of the system is. We're not going to spend a lot of time worrying about the semantics of an event or whether they differ from messages. In general, if you have a blob of JSON that you can pass around and provides useful information to other systems, that can be an event for the purposes of this talk. One of the key distinguishing features of events compared to commands is that events are observable and not directed. In a command model, each command is explicitly issued to a specific recipient. Events, on the other hand, are merely observable by other systems. So here, this guy is announcing that a customer has made a purchase and one of his co-workers is just making a mental note. Another one is going to take action and several others aren't even listening at all. What's nice about this is it means the event producers don't need to have any knowledge about who's listening to those events. This keeps them simple and allows other services to consume events without needing the upstream system to change. So coming back to our order processing example, How can this be improved with an event-driven design? Now our architecture looks like this. The order service sends events to the router, which is configured with a set of rules that determine which downstream systems get a copy of each event. There may be some targets that only care about certain types of events, or they only care about the order of a particular account. Or some may want to hear every event. Either way, the router now takes on that complexity of ensuring these events get propagated appropriately to each downstream service. And now, if another team comes along and decides they want to consume some subset of the order service events, they can just add a new rule or subscription to our event router without having to wait on the order service team to make an update for them. This allows all of these service teams to act more independently and move faster. Keep in mind, this doesn't have to be for inter-service communication. Maybe I have a really simple architecture inside of a single service, but I need an easy way to add additional operational features quickly. This brings me to Amazon EventBridge Schema Registry. So Amazon EventBridge is a serverless event bus service that allows you to easily ingest and route events from AWS services, your own applications and SaaS providers, just like CloudWatch Events, Amazon SQS and Amazon SNS. There's no infrastructure to manage or provision. Scaling is handled for you and you only pay for what you use. It has a number of native integrations with SaaS partners with more to come. And you can route events directly to different downstream AWS services, such as AWS Lambda, Amazon SQS, Amazon Kinesis and Firehose, Amazon ECS, AWS Batch, and many more. And whether events are sent from your own application or a SaaS partner's system, we make sure the event sources are properly authenticated and securely integrated with your event consumers. Now, recently, EventBridge Schema Registry was launched, which allows you to discover, create, and manage open API schemas for events on EventBridge. You can find schemas for existing AWS services, create and upload custom schemas, or generate a schema based on events on an event bus. For all schemas in EventBridge, you can generate and download code bindings to quickly help you build applications that use those events. So before we jump deeper into events and the new controls available for managing events with serverless, I should probably define a bit more about what serverless is. These are the 4 tenets that define serverless as an operational model, unless you know a better one. First of all, there's no infrastructure to provision or manage. So that means no servers to spin up, operate, or patch, and no physical or virtual or container orchestrations needed. Automatically scaling by unit of consumption rather than by server unit. Pay for value billing model. We could call this not pay for idle because it means you only pay for execution duration rather than by server unit. The fourth and final one is built-in availability and fault tolerance. There's no need to architect for availability because it's built into the service. When we say serverless, we mean it's the removal of server operations. And this is an important distinction for our customers because it allows customers to focus on building of the application rather than the management and scaling the infrastructure to support that application. AWS Lambda is a serverless product that sits at the center of a few different trends and terms, such as event-driven computing, function as a service, and it's serverless itself, which means it fits our 4 qualifiers. Lambda lets you run code without provisioning or managing servers. You pay only for the compute time you consume, and there's no charge when your code is not running. With Lambda, you can run code for virtually any type of application or back-end service, or with zero administration. Just upload your code and Lambda takes care of everything required to run and scale your code with high availability. You can set up your code to automatically trigger from other AWS services or call it directly from any web or mobile app. So Lambda doesn't just sit in a vacuum. It will usually form part of a serverless application, typically with 2 or 3 components. You have the event source, the Lambda function, and the destination for the function to connect to. The event source has a number of services that can directly interact with Lambda. That can be a change in database state, an upload to an S3 bucket, or a request from an HTTP endpoint. The function itself provides a curated execution environment with various languages built in. And now with the runtime API, you can bring any language into Lambda. The destination can be whatever your code needs to interface with. It's entirely up to you, and it depends on the business logic and the requirements of your application. The Lambda execution model can be categorized into one of the following different invocation types. There's synchronous, which is poll-based for things like inbound API calls via Amazon API Gateway. Asynchronous, which is event-based with services such as Amazon SNS, Amazon S3, and Amazon EventBridge. And stream, which again is poll-based and triggered from services such as Amazon DynamoDB or Amazon Kinesis. So first, we're going to have a look at asynchronous invocations. When a function is asynchronously invoked, Lambda queues events before a separate process reads those events from the queue and sends them to your function. Lambda manages the function's asynchronous event queue and attempts to retry on errors. If the function returns an error, Lambda attempts to run it 2 more times, with a 1-minute wait between the first 2 attempts and 2 minutes between the second and the third attempt. Function errors include errors returned by the function's code and errors returned by the function's runtime, such as timeouts. This works well in situations where every invocation must run at least once. However, in situations with large volume of errors, subsequent invocations are increasingly delayed as the backlog increases, as each new error places another retry event back into the event queue. If the function doesn't have enough concurrency available to process all events, additional requests are throttled. For throttling errors or system errors, Lambda returns the event to the queue and attempts to run the function again for up to 6 hours. The retry interval increases exponentially from 1 second after the first attempt to a maximum of 5 minutes. However, it might be longer if the queue is backed up. If the queue is backed up, new events might age out before Lambda has had a chance to send them to your function. In order to avoid this default auto retry policy, there are several widely used approaches. Function error handling with AWS step functions is something we've seen a lot of our customers use. Or using event handler for error routing logic is another thing. Some customers use third-party monitoring services for exception alerts, and these workarounds require extra resources, code, or custom logic, and can add latency to your application. What's more, retries caused by system failures due to timeouts or lack of memory or early exits could still occur. If it were possible to skip the event without retrying, it would eliminate this delay and continue processing new events. The new asynchronous event invoke controls mean that functions can now skip the processing of certain events and discard unwanted or backlog requests from asynchronous event queue without the need for workarounds. The event age control allows you to define an event maximum age in seconds, with expired events skipped to allow processing to continue. Events that do not get successfully processed within the defined age of submission are written to the function's configured dead letter queue or on failure destinations. If none is configured, the event is discarded. The retry attempt control allows you to set a maximum number of retry attempts for events before they can be skipped to unblock processing and prevent duplicate outputs. The controls are accessible from the AWS Management Console and from the new event invoke config sub-resource. For console access, go to Lambda function and click Edit in the asynchronous invocation section. And you can see here an example of how to implement the retry configuration with the AWS Serverless application model, which is an open source framework for building serverless applications. Looking again at Lambda's asynchronous invocation process, you can see that when an event is added to the internal queue, Lambda would previously only return a 2xx status code to confirm that the queue has received this event. There was no additional information to confirm whether the event had been processed successfully. If you wanted to put an event or message on an SNS, SQS, or onto EventBridge for further processing, you needed to write the handling code within your Lambda function. Now, with Lambda event destinations, you can route asynchronous function results to a designated resource without writing additional code. An execution record contains details about the request and response in JSON format, including the version, timestamp, request context, request payload, response context, and the response payload. For each execution status, such as success or failure, you can choose one of 4 destinations to send the execution record. Either another Lambda function, SNS, SQS, or EventBridge. Lambda can also be configured to route different execution results to different destinations. Previously, if you wanted to chain Lambda functions together without using an additional service such as step functions, you needed to do so synchronously. This meant the entire workflow had to complete within Lambda's 15-minute function timeout. And this wasn't very serverless, as you would essentially have to pay for idle time while your initial Lambda waited for a response. Now, with Lambda destinations, you no longer need to chain long-running Lambda functions together synchronously. Destinations allows you to return a success response to the calling function and then handle the remaining chaining functions asynchronously. You can use this to monitor the health of your serverless applications via execution status or to build workflows based on invocation results. Lambda destinations gives you the ability to handle the failure of function invocations as well as their success. When a function invocation fails, maybe due to max retries or the event age limit being reached, destinations can route the record to the destination resource for every failed invocation for further investigation or for processing. In the architecture shown here, an image is added to an S3 bucket, which triggers a Lambda invocation. The Lambda function attempts to identify the objects in the image using Amazon recognition. If that operation fails, the failure execution's results are sent downstream to an SQS queue, where they are processed asynchronously by a different Lambda function. Destinations provide more useful capabilities than a dead letter queue by passing additional function execution information, including the code exception stack traces, and to more destination services. You can use Lambda destinations in this way to build simple workflows by chaining Lambda functions where additional services such as step functions are not required. You can handle failures with additional context without having to set up custom code and logic to each function. You could add visibility and notifications using EventBridge or SNS. You could use the on-success and on-failure destinations to trigger notifications via email, chatbot, support desk tickets, or any other custom-built application. Or you can implement Lambda destinations for batching events to process with SQS or EventBridge. A couple of useful things to be aware of before you start building with Lambda destinations. Firstly, your Lambda execution role needs to have permission to access the destination service in order to pass on the event context. Second, if the execution result size exceeds the payload size limit of the downstream service, then only the invoked contexts are delivered and not the entire payload. Finally, destinations and DL queues can be used together and at the same time, although destinations should normally be considered a more preferred solution. If you already have DL queues set up, existing functionality does not change and destination does not replace existing DL queue configurations. If both destinations and DL queue are used for failure notification, function invoke errors are sent to both the DL queue and the destination targets. To configure these new controls, you can do so from the AWS Management Console. From within your Lambda function, click on Add Destination inside the Designer section. You'll then get to the destination configuration settings as shown here. You can also set these controls using SAM. You can see an example of that shown here within the Event Invoke Config sub-resource. So on to stream processing invocations from Amazon Kinesis and Amazon DynamoDB. You can use a Lambda function to process records in an Amazon Kinesis or a DynamoDB data stream. Lambda reads records from the data stream and invokes your function synchronously with an event that contains stream records. Lambda reads records from the data stream in batches via shards, which are a sequence of data records identified by a partition key. Your function is then invoked synchronously in order. If an error is returned, Lambda retries the batch until processing succeeds or the data expires. Some things to be aware of are data with the same partition key are sent to the same shard. By default, Lambda invokes your function as soon as records are available in the stream with a 1-second polar window. This means that if the batch it reads from the stream only has one record in it, Lambda only sends that one record to the function. This might not be desirable with infrequent data or during off-peak workloads. To avoid invoking the function with a small number of records, you can tell the event source to buffer records for up to 5 minutes by configuring a batch window. Before invoking the function, Lambda continues to read records from the stream until it has gathered a full batch or until the batch window expires. You can see here from the example that the batch window has been set to the maximum 300 seconds, which is 5 minutes, enabling the event source to gather more records before invoking the Lambda function. This is great for cost optimization when traffic volume is low. Batch size is still respected and will trigger on full batches before the batch window is up. And this works for both Kinesis data streams and DynamoDB stream triggers. Sometimes the opposite problem occurs in which you have a data spike and need to process shards concurrently. Parallelization factor can be set to increase concurrent Lambda invocations for each shard, which is 1 by default. This allows for faster stream processing without the need to overscale the number of shards and still guarantees the order of records that are processed. The batching is done via partition keys, which maintains the in-order processing. You can set this using the parallelization factor parameter. A setting of 1 is the same as the current behavior with a maximum setting of 10. And this works for both Kinesis data streams and DynamoDB data streams. You can see from the example here that the parallelization factor has been set to 3, creating 3 concurrent Lambda invocations for the current shard, and the consistent hashing has maintained the in-order processing of records. When processing batches from streaming sources such as Kinesis or DynamoDB, if an error is returned, Lambda retries the batch until processing succeeds or the data expires. This retry behavior is desirable in many cases, but not all. In some cases, it may not be helpful to retry, as subsequent invocations will also fail. If the function is not idempotent, retrying might produce unexpected side effects and may result in duplicate outputs, for example, multiple database entries or business transactions. Sometimes no data in the shard will be processed until the issue is resolved. This means a single malformed record could prevent processing an entire shard, since the in-order guarantee ensures that failed batches are retried until the data record expires. This is often referred to as the poison pill event, in that it prevents the rest of the system from processing data. Now, there are a number of options available to help fine-tune error handling. First, you have the maximum record age controls. This allows you to define a record's maximum age in seconds, with expired records skipped to allow processing to continue. There is a new maximum retry attempts control. This allows you to set a maximum number of retry attempts for batches before they can be skipped to unblock processing and prevent duplicate outputs. When either maximum retry attempts or maximum record age in seconds reaches the specified value, a record will be skipped. If the on-failure destination is set, metadata about the skip record can be sent to a target Amazon resource name, for example, an SQS or an SNS. If no target is configured, then the record will be dropped. This does not contain actual records, but does contain all the information needed to retrieve them. An elegant solution to the poison pill problem mentioned before is to use the new bisect on function error control. This solution means you can pull out the one problematic record and continue. It will recursively split the failed batch and retry on a smaller subset of records, eventually isolating the problematic records, meaning you are able to handle the errant record without adding processing logic. And retries do not count towards the maximum retry attempts. You can set these controls using the AWS command line interface. This example maps a function named myFunction to a DynamoDB stream that is specified by its ARN. It sets maximum retry attempts to 2 and maximum record age to 3,600 seconds, which is 60 minutes. It also configures an SQS destination ARN for function failures. So to summarize everything we've covered, we've talked about 2 types of Lambda invocations and some of the new controls available for managing them. First, for asynchronous invocations, you can use the Amazon Event Bridge Schema Registry to discover, create, and manage open API schemas for events for existing AWS services, custom-built integrations, and third-party integrations. You can manage retries to unblock processing or prevent duplicate outputs with the new controls for Lambda. That's maximum event age in seconds, which allows you to define an event's maximum age in seconds, and maximum retry attempts, the control that allows you to set the maximum number of retry attempts. You can use Lambda destinations to asynchronously chain functions together with the onSuccess control and manage function failures without coding additional logic using the onFailure control. Then we talked about managing stream processing invocations. There's batch window, which allows you to buffer records for up to 5 minutes to avoid invoking your Lambda function with small number of records, which can be great for cost optimization when traffic volume is low. We covered how you can customize your shard processing concurrency using parallelization factor to achieve faster stream processing without the need to overscale the number of shards. We spoke about how to eliminate the poison pill problem by using bisect on function error control to unblock your stream processing by isolating the one problematic record. And finally, I discussed how you can manage retries with maximum record age to skip the processing of old records and maximum retry attempt to specify how many retries to perform on a given record. And finally, the onFailure destination to send metadata of a failed record to SNS and SQS. So that's all for this Tech Talk. Thank you for sticking around to the end. I hope it's been a useful and informative session for you. Thanks again.